Let me start out by telling you that the topic I'm going to discuss is really quite new to me, even though my very first job after I got the PhD was at the ESSO Research Laboratory in Linden, New Jersey. That's the precursor of a small oil company now known as ExxonMobil. And there I worked on lubrication and combustion problems mostly. But on Thursday evenings, we got together for a bowling, know each other, and there were people there from all sorts of divisions. And I talked to the recovery people, to the exploration people, over bowling balls, if you allow the phrase. And the kind of comments that I heard is that everybody knows where oil comes from. We've known it ever since we've even thought about the subject. And it comes from plants. It took billions of years to process the oil, but it's definitely a biogenic product. And then, of course, I sometimes asked a more detailed question: how do we find how do you find the oil? How do you know where to prospect? Oh, he said, we have wonderful geological exploration tools. And besides, before we commit large amounts of money, we always call somebody in who knows how to use the divining rod. So that's really my background in this field. This field is very controversial. It has a great deal to do with long-term estimates for global warming. It has a great deal to do with what we pay at the pump. Every day you hear the following kind of remarks, almost every day. Oil is approaching an all-time high per barrel. Well, is it? That's clearly a statement that requires a little clarification. If you look at constant dollars, in 1985, $35 per barrel would today be $84 per barrel, which I think is a little more than $75 per barrel. And of course, our estimates on where the oil price was going then was very much higher than $35 per barrel. We were talking about $80 per barrel in 1980. So let me just assure you that you're not overpaying for the oil. And that's got nothing to do with my background in the oil business. It's just simple economics that gives us that number. The topic I want to discuss involves a controversy that bears very heavily on future supplies of petroleum, future supplies of low-cost petroleum. I have very little to say about that because the answers there are not clear. For about 50 years, there has been a significant controversy between the way the Russians look at oil supplies and the way we look at oil supplies in the West. There is a small problem here. Some of the Russians can read English. Almost none of the American scientists read Russian. So the Russian literature was really almost unknown to us until just a very few years ago. We did get a glimpse of what the Russians were up to from an astrophysicist, Tommy Gold, who wrote a nice little book on the hot, deep Earth. We didn't know that he was just plagiarizing the Russian work. He did that pretty well, and the Russians are very upset over this little side issue that here was an astrophysicist taking the Russian ideas and popularizing them, I think, very much as his own, because he never refers to the earlier work that was done in Russia. Now, what is the difference between the Western and the Russian-Ukrainian viewpoint? It's known as the RU theory. In a nutshell, we say oil comes from plants and it's sort of being exhausted, particularly the low-cost oil. The Russians say, or the Russian and Ukrainians say, that is false. Oil is an abiotic product. It's formed near the mantle of the earth. It is, in fact, a renewable resource. It's not something you're going to ever run out because it's being made all the time. And we want to examine the science back of this assertion and what has happened during the last few years following the publication of a very nice paper in the Proceedings of the National Academy of Sciences by Russian authors defining the RU theory. And this is the main subject of my topic here. Now, there is a great deal of peripheral evidence that oil does not come, or organic compounds do not come from plants only. We know all about meteors, asteroids, comets, planetary atmospheres other than our own. Wherever we look, we find organic compounds. These couldn't possibly be plant-derived. There is something going on synthesizing this stuff that does not involve plants. That is certain. I don't think that's a controversial issue at all. I will go through some of the historical development which has medical implications, as you will see, of our ideas about where the oil comes from. And the Western view has led recently to many people, particularly oil experts, telling us that we are imminently going to run out of low-cost oil within, I've seen predictions of 15, 20 years will be peak production, and that'll be the end of it. It could be the end of it if it were not being produced all the time and refilled somewhere within the bowels of the earth, within the mantle of the earth, and then trickled up from there to the surface where we can recover it. That's really an important issue. Are we really conceivably running out of oil? Of course, that statement's completely false anyway, because it includes only the low-cost oil that we know about now. It does not include oil recovered from shale. It does not include tar sand oil. This happens to be a field in which I worked for many years, and I will refer you to some of the literature on that. These resources are probably at least 100 times larger than the conventional oil sources, and we're not going to run out of those. In fact, I think 3 years ago I made an estimate. I probably gave a lecture on this topic at this meeting on just how much fossil fuels we had available and how long they would last if we had 10 billion people on the planet and all of them enjoying the standard of living that we enjoy in the United States. And I think I said something like 400 to 500 years, and that is still my estimate. That's certainly the minimum amount of this fossil fuel resource that is available. But at what cost? At what environmental impact? These are some of the crucial questions that need to be discussed. So I have said the essential point that I want to illuminate now in some way, namely the Russian uranium theory and what the evidence is in support of that theory. And my final statement here is that the abiogenic production of petroleum is supported by the second law of thermodynamics. That's one of the foundations of science developed during the 19th century. We have never found any disagreement of any quantitative study that has been done with this theory. And, you know, we all have firm beliefs. I happen to be a firm believer in the second law of thermodynamics. And as the result of that, since the Russian abiogenic theory has been demonstrated to be consistent with the second law, I have to accept that. This simply says that there is non-plant production of petroleum. Does it mean that there is no production of petroleum from plants? Well, I made an unfortunate statement in my article in which I said that it might be that there could be a discrepancy in the Western theory with the second law of thermodynamics. But that's a false statement, because there isn't any Western theory. There's a Western hypothesis. There's no Western theory about how petroleum was formed. So we really don't have a disagreement. We just didn't read their literature, so we didn't understand what the real mechanisms are. Now I'm going to begin with a history of petroleum. This is very important to understand. It's been around a long time. Egyptians used pitch derived from petroleum to coat mummies. I'm not going to go through all of this, just some highlights. The Old Testament tells us that Noah used pitch to make his ark watertight. The Emperor Charles V swallowed petroleum to mitigate the severity of his gout attacks. As you can see, there are medical implications to this study. I don't know that petroleum is used to control gout today. I somehow doubt it. Until the end of the 19th century, petroleum was taken by many people in many lands as a universal cure or palliative for many ailments. That's part of the medical history of petroleum, probably not a part that the physicians in the audience are very proud of. The modern petroleum industry, as you know, began in 1859 with drilling of an oil well by Edwin Drake in Titusville, Pennsylvania. The well flowed at the rate of 35 barrels per day. The initial cost was $20 per barrel in 1859 dollars. Now that's a big price for petroleum. I would say something like upward of $2,000 per barrel. Well, we are not there yet. Now let's look at the Western wisdom, the history again of petroleum. And I thought a good place to begin is the Encyclopedia Britannica, the first edition, which was published in 1771. And this has no information on the origin of petroleum. This was not of any particular interest at the time. What we find is some very interesting physical descriptions of petroleum that fascinated people in that time period. Petroleum is called rock oil. It's very subtle and penetrating. It's much the thinnest of all native bitumens, or bitumens, whichever way you want to pronounce it. This is English. I ought to use English pronunciation. It is very light and very pellucid. Does anybody know what pellucid means? It means transparent. That's all it means. I didn't know that word, but it's still in Webster's dictionary. Though equally bright and clear under all circumstances, it is stable to a very great variety in its color. Here's an interesting statement. The white petroleum is most esteemed. It is so very flammable that while it floats on the surface of water, as it does in many parts of Italy, it takes fire at the approach of a candle. And then here we have a statement where it is found essentially everywhere. And here we have the medical wisdom of 1771. It is principally used externally in paralytic cases and in pains of the limbs. At least they aren't drinking it anymore there. Now, I do need to refer to time periods, and I just want to give you a little summary of the tail end of this geological time and formation period. The Archaeozoic period, which extends from about 1.5 billion years back, was not characterized by either animal or plant life. If we find petroleum in Archaeozoic rocks on Earth, they cannot possibly be formed from plant or animal life because there wasn't any. If we go to more recent time periods, then the idea that these biological organisms were responsible over long periods of time for decomposing and somehow producing petroleum, that at least has geological support in that it is conceivably possible that that's how it was formed. I will not use this chart otherwise, that's only for that purpose. Now I want to say a few words about the abiotic organic compounds and the RU, the Russian Ukrainian theory. This was, except for Tommy Gould's Hot Deep Earth, a closed subject to us, or to most of us who don't read Russian very well or are too lazy to read Russian literature on this subject. The Russian literature goes back over 50 years. In fact, it goes back much longer than that, because Mendeleev, the inventor of the periodic table, talked about more than 100 years ago about the formation of petroleum from elements not involving plants. So the idea really goes way back, but the hard work, the scientific work in the RU theory is about 50 years old. We finally got a glimpse of what this work was all about when, in the year 2002, in the Proceedings of the National Academy of Sciences, a Russian article was published by some reasonably well-known, I shouldn't say that, in the West barely known, but in Russia very well-known, petroleum experts, scientists. And these people are listed here. The senior author is J.F. Kenny. He is associated with both a company in Houston, Texas, and is a member of the Russian Academy of Sciences. A co-author is Kucherov from the Russian Academy of Sciences, Bendelani, Russian State University of Oil and Gas, and another scientist, Alexeyev, from the Russian Academy of Sciences. The name of the article is The Evolution of Multi-Component Systems at High Pressures, 6, the 6th paper in a series, The Thermodynamic Stability of the Hydrogen-Carbon System, the Genesis of Hydrocarbons in the Origin of Petroleum. This deals with the science of how petroleum would have formed in the absence of plants. And that's what we want to take a look at now, except for a brief comment on the subsequent history. This 2002 paper, appearing in a prestigious Western journal, prompted many people to look at this stuff finally, and included in there was a group at Harvard, 7 authors, one of whom, Dudley Hirschbach, is a Nobel laureate in chemistry. I mention that because to some people that somehow makes everything true that may be said. And they confirmed, or they performed experiments showing that in order to produce methane, they needed very high pressures, 5 to 11 gigapascal, temperatures of 500 to 1,000 degrees, conditions near the mantle of the Earth. And they did laboratory experiments, and they verified that they could produce methane, which very easily is converted into petroleum. I'll say a few words about that in a moment. And they therefore produced petroleum without plants. The summary is, the study demonstrates the existence of abiogenic, sometimes called abiotic, meaning without plants, pathways for the formation of hydrocarbons in the Earth's interior, and suggests that the hydrocarbon budget of the bulk Earth may be larger than conventionally assumed. Now that's quite a statement coming in the Western prestige literature with a signature of a Nobel laureate in chemistry who presumably understands thermodynamics as well as it must be understood if you want to work in that field. But this isn't the only example. Earlier this year, Roald Hoffmann, another Nobel laureate in chemistry, wrote an article called Old Gas, New Gas, and he developed a mechanism on how the methane was initially formed from non-organic materials. And the pathway I won't discuss. It involves reactions of solid rocks, olivine, forming serpentine, and then finally involving the formation of, from olivine with water, serpentine, brucite, magnetite, and hydrogen, and then followed by what we know as the Fischer-Tropsch synthesis for chemical compounds, very well known, widely used in the petroleum industry, synthesis to make methane. And once we make methane, we have no problem. Methane is, of course, the main ingredient in natural gas. Once we have that, from methane we can form all of the other compounds. And that is the essence of that Russian paper by Kenny and his associates. Now let me say a little bit about the science that is discussed in this paper by the Russians. This is a thermodynamic paper. It is a paper involving the question, how do we go from methane to the hydrocarbons that are in petroleum? What is the mechanism? How will this occur? And what they managed to show, using the best laws, scientific laws that we have for addressing a subject of this type, that it took high pressure, the kinds of pressures that we never have near the surface of the Earth, high pressures and temperatures. Without the high pressure, which does not exist near the surface, you cannot form these petroleum-like compounds. That is the essence of the analysis that they publish, this article labeled 6. If you are at atmospheric pressure or anywhere near it, near the surface of the Earth, you cannot start with methane and produce petroleum-like compounds. You must have the high pressure, but the high pressure is never at the surface. So even if you allow for the tectonic movements and the stresses and strains over billions of years that occurred near the surface, you still cannot make petroleum. That's the essence of that paper. You can only make it if you are far down in the Earth, where the pressures are high. And that of course, says that the plant origin of petroleum is not really based on science. It's a hypothesis that's unverified. But when I say that it may actually be a problem for the Western hypothesis, I really can't be sure, because I don't know what all the bacteria and all the other possible transformations near the surface would have done. So I don't really have a mechanism or a theory for saying the Western view is wrong. It's just not proved right. There's a difference there. I don't know that it's wrong, but I have no way of knowing how you might justify the Western view that petroleum is formed from plants over long periods of time. There were no geologists around during these few billion years when that would have happened. And if they'd been around, it's not sure they would have done the right kind of science. So the fact is that we have a mechanism for forming these petroleum-like mixtures that requires the pressure and temperature near the Earth's mantle, deep down. The minimum pressure, if you look at the science part of this article, must be somewhere near 50 kilobars, of very high pressure and reasonably high temperature. Now, the Russian-Ukrainian versus Western dialogue has had an interesting history during the last few years, as you might guess. And here are some nuggets from this dialogue. They're sort of interesting. The Russian-Ukrainian view is the J.F. Kennedy view on the left, and the opposing Western view is the Richard Heinberg view. The Western view is some molecules found in petroleum look like molecules found in biological systems and must therefore come from these. Those are called biomarkers. And I think that we heard in the last lecture a little bit about correlation doesn't mean causation. I'd like to apply that theorem here. There is a correlation, but it doesn't imply causation at all. Just because there are some molecules found in petroleum that look like molecules found in biological systems doesn't mean one comes from the other. The Russians are less charitable on this issue. They say this is clearly wrong, and what they claim is that you could argue that elephants have ivory tusks, and then you look at a piano, it's got ivory keys, and therefore you conclude that elephants are descended from pianos. That's roughly that kind of logic. Now then there are some other nuggets here. Odd, even carbon chain imbalances are all consequences of the structures of multi-component fluids at elevated pressures, up to the pressures for diamond formation, and support the idea that these compounds were formed at elevated pressures. That's the Russian view. The Western view, odd, even carbon chain imbalance, carbon isotopes ratios, optical activities of molecules are petroleum markers resembling those of biological systems. That's the same argument as the first one. If it looks alike, it must be coming from there. Well, I mentioned that we find carbonaceous compounds in meteorites and in many other, in asteroids, and even in planetary atmospheres on planets other than the Earth where there were no plants ever grown. So that doesn't prove much of anything either. Then there is a statement about, in some of the Western literature, that there is a carbon-13 to carbon-12 ratio. It indicates biological origin. Now that's pure nonsense, because the carbon-13 and carbon-12 react differently. They disappear differently, depending on the environment and the history. So whatever that ratio is determined by the history prior to our looking at it, rather than by any kind of intrinsic physical law. Well, these are sort of some highlights of what the controversy is all about. The key scientific issue, I have mentioned it, it's compatibility of the theory with the laws of thermodynamics. The RU theory with abiogenic petroleum formation is quantitatively described in the paper by Kenny et al. The thermodynamics is very well done. In fact, I wrote a book on thermodynamics once, so I'm qualified to make that statement. I found the article to be very, very challenging and spent a great deal of time looking at that aspect of the article, and I think it's very sound thermodynamics. We don't have anything like that in the Western literature. It is unlikely, in my opinion, that such a model could be constructed without having the surface conditions on the Earth duplicate what the mantle conditions were supposed to be, especially the high pressure. You just can't get that anywhere near the surface. So I think it will be very challenging to reconcile the two views, although the Western literature lately has many attempts at doing this. Now I want to say a few words about running out of petroleum resources. There was a long period of time when I did really nothing but run this Department of Energy Fossil Energy Research Working Group. I was chair of that for 8 years, from 75 to 83. And during that time period, I had a very large group of collaborators. These were typically experts from the oil industry, academic experts, and also government people who were concerned with these topics. And we spent an enormous amount of time trying to understand the background material that might be available for unconventional oil recovery. There were large investments made by the US oil industry in learning how to recover petroleum from shale, for example. My recollection is that the precursor of ExxonMobil Corporation alone spent some $2 billion in Colorado, in the Piceance Basin of Colorado, building recovery systems. There is a problem with developing a new high-cost recovery. And that is, I think, the main reason why we don't have unconventional oil resources in the market today. The problem is that we can build these systems, we can extract oil, but they come from an unconventional source with the recovery ratio and energy in to energy out ratio fairly small, like maybe 1.2 to 1.4. That is, we get 20 to 40% more energy out than we put in recovering oil from these unconventional sources. And at the same time, there's still conventional oil all over the globe. All you have to do in the right places, in Saudi Arabia or in Iraq, if you don't get shot, to sink a small amount, a small hole near the surface, and the stuff gushes out. And you can see what would happen if you made a multi-billion-dollar investment in this new technology, and the people who have the conventional oil wanted to put you out of business. They'd put you out of business overnight. That's clear, because they have essentially zero cost compared to what it costs you to make these synthetics. I think that's the main reason why we haven't done it. It's not that it isn't there. It's not that we don't know how to do it. Shale oil recovery is an old technology. It's been used all over the globe. The Chinese did shale oil recovery around the beginning of the 20th century, around 1910. How did they do it? Well, they had a process developed by the Chevron Corporation that they used very successfully in recovering oil from shale at the beginning of the near the beginning of the 20th century. And then, of course, when we were in the middle of learning how to do this unconventional recovery, there were these environmental issues that surfaced. Some of them were real and some of them were not very real. I remember a question about how to dispose of the ash, and we had all kinds of cancer problems potentially that were going to happen to all the people who were anywhere near these shale processing plants. And when we went to China and looked at what was happening there, well, they'd been doing it for about 100 years already. What did they do? They just spread the stuff together with fertilizer on their farms, and the areas where they did this were essentially free of cancers of all types. It just didn't happen at all. In fact, instead of being a cancer-causing chemical, it was a cancer-preventing chemical. But we didn't know that, and because of that, there was some serious impediment to going ahead for environmental reasons with this type of unconventional recovery. Shale oil is our most widespread and largest potential unconventional oil source. But there are others. There are the tar sands, particularly in Alberta, Canada. These tar sands have been widely used. The cost for the tar sand oil was around $20 a barrel in around 1980, 75 to 80. And that recovery continues to this day. But there were problems there too. There were environmental problems. They didn't quite know what to do with the processed material, and at the time they disposed of it in wells all around the mine. By the way, that's a lunar landscape. If you ever have a chance to go to Fort McMurray in Canada and take a tour of the recovery of oil from tar sands, it's a wonderful thing to look at. But these little lakes that they created around the plant, they were not such a wonderful thing, because the migrating birds that flew over didn't know that that was not potable water. There was no sign telling them that. So they landed there, and then there was a substantial loss of bird life, which was handled at the end by having little cannons around the lakes, which were regularly shot off during the migratory season, and that did a pretty good job of convincing the birds not to land on these lakes. So there are environmental issues that we do and do not understand here that remain to be resolved. On the other hand, the recovery of oil in the Alberta tar sands continues to this day, and I don't know the exact final or current value of the production, but it's very large. It's something probably approaching 1 million barrels a day. That's like a good-sized oil well, a very good-sized oil well. And it is certainly economically competitive with $75 a barrel oil. We started out at $20 a barrel then, and if you use your inflator, that would be around $40 a barrel in today's dollars, which is much less than what we are paying on the international market. In other words, these unconventional oil sources ought not to be written off as something that will allow deferral of peak oil production by a short period of time. That is just plain wrong. These unconventional oil sources sooner or later will be developed, and they will be much cheaper than the plant-based, the solar technologies, and any of these alternative sources that have been around for a very long time, really. I used to work in that field, and I found that, well, let's look at the history. When Jimmy Carter was president, Jimmy Carter rolled up his sleeves and he came to his committees and he said he was a nuclear expert, and he said, let's do everything. And we did. I mean, every conceivable new energy recovery system was considered and developed and supported preferentially with low taxes and dollar amounts. And this goes back now 30 years. And in the 30 years, how much unconventional energy has penetrated the market? Well, something close to 1%, and that's it. And if that's all we could do with favorable support, it says to me that the economics are not right for these renewable resources, that they are not going to replace even high-cost oil, if you call current oil high cost, which it really isn't. And you're certainly not going to replace low-cost nuclear energy, which is also certainly a very, very desirable alternative to these renewable resources. I think it's maybe the third or fourth time that we are on this renewable kick, and it probably isn't going to go very far. Now, this is essentially, I think my time is up, isn't that right, Arthur?
No, you still have 20 minutes.
Oh, I still have 20 minutes. Well, I don't know how that, that can't be right. I think that there is a break that you were just giving.
The break starts at 10:30 and goes to 10:45.
Okay, fine.
You started at 9:30.
Yeah, I thought I was supposed to talk for 45 minutes. According to that schedule, I've just used...
An hour. It's an hour.
Including questions, yes.
An hour including questions.
I want to say a few words about oil recovery as it is done now, and compare this with what would be oil recovery on the Russian-Ukrainian model. Fundamentally, the production of the precursor, the methane, and then the conversion of that to petroleum-like mixtures occurs deep in the earth, like at least 100 kilometers below the surface, according to the Russian-Ukrainian model. That's a long way. And we are nowhere near we have nowhere near the technology to drill into the earth to depths of this type. That's far beyond our capability. I think the deepest we go is something, maybe a tenth of that in the sea off the western coast of South Africa, That's the deepest drilling recoveries that we probably have currently for actual oil production. I don't see any hope of ever drilling with conventional technologies to depths of this sort. The Russians claim, and I have no reason to disbelieve them, that their model has helped them to find new oil in Russia. And they're very proud of the fact that during the last 50 years, they have used this oil to make Russia one of the main exporters of oil to the world. It's not really clear, and I've tried very hard, as have some of my colleagues, to find some real examples of how the Russians used their newly found wisdom to find a great deal more oil. There are some examples that I can think of. First of all, we would not drill in Archaeozoic rocks in the past because we would not think there would be any oil in there because there were no plants and animals there. And the Russians certainly did drill there. But I don't know whether all of their new discoveries were from rocks of that type. That is not said. There is an institute in Vienna, near Vienna, in Luxembourg, that was founded by John Foster Dulles and Mr. Molotov. Very interesting collaboration. It goes back to the 70s. They got together one day and they were both sober and they decided there were some problems bigger than the East-West conflict, and they converged on two topics. One is world's food supplies, and the other one is world energy supplies. The energy studies at the Institute were run by a German scientist, a nuclear scientist, Wolf Hefele, actually a good friend of mine. He came to our university as a Regents professor and lectured there. And I was deeply involved in this program with the Russians because I was at the time the US member of the steering committee for the energy studies at YASA. And I met many Russians at the time. My Russian was good enough to say I don't want any more when I went to dinner, but I really didn't really understand what they were saying about unconventional oil. And I've tried in recent times, just during the last few months, by writing to some of my colleagues there, or former colleagues there, to find out what examples they could provide on using the RU theory that led them to drill at a place where very large amounts of oil could be found, or were found, that did in fact produce this conversion. And at this point in time, I'm left without an answer to that question. They say they did it, I don't know where, I don't have the concrete examples that would help to do this. This is the same references I had, the alternative oil sources. Oh, this is the example that I cited the result of a while ago. From 1980 to 2006, the purchasing power of $100 declined to about $41.43. That's an actual number coming from the economists who study this problem. In 1980, refined shale oil was estimated to cost around $35 a barrel. Therefore, the 2006 cost, and this neglects technical improvements over a 26-year period, should be about $84 per barrel. Then there is the similar number for the tar sands that comes out to $48 per barrel, and I've already said that would be economically competitive. During just the last few months, the US government has leased a variety, or has offered support for a variety of small companies looking at Arkansas shale and Texas shale and also Jordanian shale to see whether or not some new recoveries of unconventional oil were now economically viable. So let me summarize then the scientific issue and the recovery of abiogenic petroleum at depth. The scientific issue, as I have said, is the model that we use compatible with the science that we know. And the RU theory, as applied by Kennedy and by Kenny, almost said Kennedy. I wish it were Kennedy. As applied by Kenny et al., is soundly based on the laws of thermodynamics. I gave some numbers here on occasion in units that you may not be familiar with. I referred to pressures which are normally to us in everyday life given in atmospheric pressure values, 14.7 pounds per square inch. They can be also given in bar or in Pascal, and this is just a simple way to make those conversions. I have said that the final section of the paper by Kenny and Company is an experimental demonstration of the formation of hydrocarbons at pressures up to 50 kilobar and temperatures up to 1500 degrees C. These are typical mantle conditions. The final conclusion is that depths of at least 100 kilometers below the surface of the Earth are required for petroleum formation from elementary carbon, hydrogen, and oxygen. We have some experience with some practical field experience that suggests the validity of the Russian theory. To begin with, there is finding oil in Archaeozoic rocks. That's a very important point, that there are rocks that antedate the formation of animal or plant life on the planet. Also, there is a famous drilling and recovery experience at Green Island in the Gulf of Mexico. This was a vital, usable oil field, was very carefully assessed. We drilled in there, we got our oil out, and according to plan, just the way it was supposed to come out. And then we forgot about it and then went back about 20 years later, and lo and behold, not only was there oil at Green Island in the oil field, there was a lot more there than we had when we began. Where did that oil come from? Well, according to the RU theory, this is trickle up from formations deep in the bowels of the Earth, the way all the oil probably, or possibly, according to their view, got to the surface of the Earth. There's a compelling experimental example of field experience supporting that view. There may be others that I don't know about. Now, just how to profit from the RU theory, except by being more generous in the selection of the oil fields that you attempt to drill in, is what I say a little bit of a mystery. I don't believe that the divining rod will be of any help there. I think what we really need is to understand the examples of the fields that have been discovered and developed in Russia since the Russian theory has been used as a guide for oil recovery. So let me conclude then by reiterating the statement that we are not running out of oil. There is plenty of oil all over the globe. The price of oil is not determined by the availability of the material. It's determined by political factors. It is determined by perhaps political impositions against producing the material at the lowest possible cost. There certainly is a problem with low-cost oil and minimal environmental impacts that we want to have, which may rule out very large-scale shale oil production or production of oil from tar sands in the manner in which we tried to do it some 40 years ago. We maybe need better approaches to this sort of recovery. And most important of all, I think we need to accept the fact that using more oil is not going to wreck the planet, so that we have impediments that have nothing to do with oil availability and oil use of the sort that were discussed during the first few lectures this morning, that maybe this stuff isn't ruining the planet if it just burned properly and we only get additions of CO2 that are basically small compared to the natural variability of CO2 in the environment. And I think I'll close with that remark. I know my time's more than up now, Arthur.
I have two questions. The first one is, what was the specific process that was used by Exxon to attempt to extract the oil from oil shale, and was it a proprietary process?
There were several processes used. It was usually in situ recovery, which means that there were columns of the material broken up in adjacent areas. I think I'm describing the Tenneco system mostly, because I don't really remember whether there was any difference between that and the Exxon process. But the idea is that you take the shale, you crack it, and then you cook it. That's really, in a nutshell, what you do.
So they were essentially incinerating it? And
exactly.
The gases and condensing it?
That's exactly it.
Okay. The second question I have, do we have any estimates on the amount of biogenic oils that have been found in depleted oil fields?
Well, we don't really distinguish between biogenic and abiogenic at the recovery problem. Think of it this way. There are rocks near the surface. They've had tremendous upheavals over billions of years. They've cracked. There are rock formations. And somewhere, somehow, these are capped fortuitously. And we form this stuff at depth, and the stuff diffuses up slowly from one layer to the next, and ultimately gets trapped at these top rocks, at these top layers that are formed, which are caps for the diffusion of the oil. And when we then drill from the top, that's what we find. On this RU model, it all comes up like this, because they say you can't form it near the surface. So the Green Island experience is a very good example of what is predicted according to the Russian theory, the Russian-Ukrainian theory, that there's capture of oil produced at depth, which works its way up slowly to the surface. That's what we drill in, and that's what we see.
Okay, but can we then assume that if there is a depleted oil field, if it starts to fill up again, that oil is a biogenic oil coming up?
Well, but you see, there is a time question involved in what you say. You're saying essentially, once it's empty, it ought to refill. But you know, it's taken billions of years to fill these things. And that's a little bit beyond our planning horizon as humans. We're not going to sit there for billions of years and wait for it to come up again. And that's you know, the $100 question. What can you do to stimulate this flow? Is there some simple way that you can accelerate it? Nuclear bombs won't help you, because you can't make shaped charges with those. If Edward Teller were here, he would say that's the way to go, because the Plowshare program allowed us to do drilling on an unprecedented scale. But what is wrong with that? It's drilling in a spherical system. It isn't going right where we want to go. The time that is involved here is unclear. And that's why I say we want to understand what the Russians mean when they say because of their theory, they were able to find many new oil fields, and I don't have an answer to that. They haven't told me. We're still trying to find out.
Thank you very much.
Bruce Haynes, UC Berkeley. There seems to be a gap, or at least you didn't discuss one thing that's bothering me. Where does the carbon and the hydrogen come from? Is it known that there are enough carbonates in archaic rock?
Absolutely. First of all, I'm glad you asked that question. What is the carbon dioxide balance at the surface? Arthur mentioned Bill Nierenberg. The last time I heard someone talk about that subject, he said, we know how much carbon dioxide is generated, but we don't know where it's all going. We know how much the plants take up. We know how much goes into the ocean. But there is a surplus, which may be diffusing back the other way. So there may even be a CO2 input slowly going opposite to the flow of the oil. I don't know the answer to that. Maybe someone here has...
But do they find a lot of carbonate
yes,
in archaic rock?
Yes, the Roald Hoffmann example that I gave involved reactions with rock that you find at depth. The source of the CO2 was archaic rock.
And what about the hydrogen? Where is that?
Water. The hydrogen is water.
But is there enough water?
There is apparently there is a lot of water as you go down. I mean, if there are holes in the earth to allow the petroleum to come up, there must be holes in the earth to allow diffusion of the water in the other direction. And also many of these rocks are hydrated rocks, so there's probably even formation because of the presence of hydrated rocks.
So one thing that might discriminate is that if you do find oil in archaic rock, then that the Western theory has to explain that. And if the Russians, they must know whether the rock they're drilling in was archaic rock or not. So there should be some evidence out there.
Well,
that there's as much oil coming from archaic rock as from non-archaic.
There is oil coming from archaic rocks. There are several examples of finding oil at rocks of very considerable age. I mean, that's really the question you're asking. On the other hand, it's almost fortuitous when we find these rocks at the top, because that's not where they come from. The upheavals brought some of this stuff to the surface, but not enough to allow us to convert to archaic rock drilling at the surface as a source of oil. So the whole thing is a dynamic process still. And I think that there is a hole there. I said, I don't really know which particular discoveries made the Russians rich in oil. They haven't told us. They just said they've done it that way. And the evidence is there that they've done it because they are exporting oil. There's no question about that.
You said that you talked about the economics of recovering oil from the shales and the sands. That's very important, of course. But there is another question that I didn't hear a comment on. Suppose you could do it economically, but suppose that your energy recovery is less than reasonable. It's the same problem we have with ethanol. If you put enough subsidies into making ethanol, you could make it cheap. But
well,
you have to put more energy in than you get out. There's no point in it.
Well, these cost estimates that we had in the 70s, I mean, I have to assume that the oil companies would not invest billions of dollars if they did not expect to get some kind of a return on that. And the investments at the time were quite large, involved many oil companies, not just Exxon. Chevron was involved in it, Tenneco was involved in it, and shale oil recovery has been done all over the globe for many years, and it has not had enormous subsidies, so that it must be somehow marginally competitive. But marginally competitive with what? What is the price of oil? You mean you go to the Middle East and you sink a pipe and the raw oil comes out for what, 60 cents a barrel? I mean, that's one kind of a price. But it's not the price at which the country sells it. There are costs levied by the owner of the well, of the land. There are costs levied by the companies who bring it up. They have legitimate costs. And of course, finally, before we burn it, it has to be upgraded. So there's a long process that raises the price significantly. And is this marginally competitive today? Well, I gave you one example where it is, which is the Alberta tar sands. They've been making commercial recoveries at least for 40 years.